Welcome to this session on the Decadal Survey on Astrobiology and Planetary Science, or Planetary Science and Astrobiology, as the report title says. I'm David Smith. I was the study director, and I will be introducing our speaker, Robin Canup, Assistant Vice President of the Southwest Research Institute, who was one of the co-chairs. The other co-chair, Phil Christensen from Arizona State University, sends his apologies. He's actually at JPL today, delivering his instrument for Europa Clipper. So, Robin, why don't you take it away?
Thank you. It's a pleasure to be here and to get to present some highlights from our recent decadal survey that was released in mid-April, particularly those that we think will be hopefully of most interest to this group. So our process is defined by what's called the Statement of Task from our sponsors, NASA, Planetary Science Division, or PSD, and National Science Foundation. Compared to the prior decadal survey in our field, we too provide an overall synthesis of the state of knowledge, identify the top research questions to be addressed in the next decade, and prioritize various research activities and in particular missions to best address those questions, as well as recommendations related to overall programmatic balance, technology and infrastructure development needs, and decision rules to address any budgetary changes. Key distinctions of the report this time include consideration of the state of profession and issues of diversity, equity, inclusion, and accessibility. Our report, for the first time, is organized by overarching scientific questions and topics rather than by destination in the solar system. As our title indicates, we have a much greater emphasis on astrobiology. We also included discussion of planetary defense and an extensive discussion and awareness of human exploration plans and how they interact with planetary science and astrobiology goals. The structure of the survey shown on the left, we had a steering group and 6 panels based on destination, but the structure of the report shown in the middle, again, is by overarching priority science questions and by topic. So each one of those boxes in the middle indicates a different chapter in the report. Each chapter was drafted by a writing group, the writing group being comprised of members of both the steering group and the panels that had relevant interest and expertise. The highest level recommendations in the report are contained in the programmatic chapter, that's chapter 22. It's a quite large report, over 700 pages in total. I point you to a table at the very beginning of the report that gives a detailed guide by topic on where to find things in the report. This is our steering group. This was our leadership group responsible for the top-level prioritizations and recommendations with expertise across the scope of our scientific, technical, and policy task. And they, as you can see, included multiple people with strong astrobiology background and expertise. Here are the membership of our 6 panels. And the first name listed in each is the chair of the panel, and the vice chair of each of these panels was also a member of the steering group to guarantee communication between the panels and the steering group. A couple notes on our process. We started just after the pandemic began. This decadal was the only one conducted entirely remotely. We received more than 500 white papers. That was about twice the number received in the prior planetary decadal. We had a great number of all remote meetings. You can see the numbers here, more than 150 panel meetings, more than 20 steering group meetings, most of those multi-day, with more than 300 presentations by external speakers. The list here indicates some of our main milestones in our process. A big part of our process was reviewing prior planetary mission concept studies that had been performed before the decadal started, as well as identifying and conducting new studies as part of our as part of our process, ultimately supporting our mission prioritizations. But a fundamental step of importance in this process was the initial identification of the priority science questions that would form the structure of our report, which again was organized by priority science questions for the first time. That was the first activity of the steering group, and what you see on the screen now are the 12 priority science questions that were ultimately identified by the committee. They're grouped into 3 scientific themes. The first is origins, and this covers 3 scientific questions, or as we've defined them: evolution of the protoplanetary disk, the formation of planetary building blocks, accretion in the outer solar system, origin of Earth, and the inner solar system bodies. Theme B, worlds and processes, relates to the diversity of objects we see in the solar system today and the processes that have affected and continue to affect them in some cases today since the primordial time. This spans impacts and dynamics, solid body, interior, surfaces, atmospheres, climate, giant planet structure and evolution, and the uniquely coupled circumplanetary systems. Theme C, life and habitability, has 3 priority science questions: the issue of how life on Earth originated and evolved, the concept of habitability, including how it can change with time, and finally, question 11 relates to the search for life elsewhere beyond Earth in our solar system. Question 12 is a cross-cutting question on exoplanets. We say it's cross-cutting because it relates to all of our other themes. So for each of these 12 science questions, there's an accompanying chapter in the report. They're substantial chapters, and indeed the science question chapters comprise roughly the first 350 pages of the report. So each of these chapters was written by a dedicated writing group, and they have a common format. They start off with the priority question, then they identify the major, typically half-dozen sub-questions that are the most important ones currently. But the report goes beyond just identifying the questions and sub-questions that we want to see answered. For each of those main sub-questions, the report also identifies specific strategic research activities that would be of highest priority for advancing our understanding or answering that question in the next decade. So the strategic research, these are particular data, observations, theoretical models, laboratory or experimental work needed. So we hope these science questions, in addition to providing the intellectual foundation for our prioritizations within the Decadal Survey, will also be of broad use to the community, allowing researchers, for example, to immediately couple specific observations or modeling efforts back to the priority questions. So once we had drafted these 12 chapters and you looked at them as a group, there were a handful of key high-level themes that emerged that I'll list here. The first is the crucial role of both sample return and in situ analysis for providing breakthrough science and ground truth constraints. The relative dearth of knowledge of our ice giant systems, especially in light of our knowledge now that they may be the most common type of planet in the universe. The importance of primordial processes to establishing initial compositional reservoirs in the disk, the planetary building blocks, the early dynamical evolution of the solar system, and of course the extensive and complex interplay of internal and external processes in shaping the worlds we see. Central importance, understanding the varied evolutionary paths of our terrestrial planets, and the central question of how life on Earth emerged and evolved, and the compelling rationale to study habitable environments on Mars and at icy ocean worlds in particular. And finally, the desire this decade to make substantial progress in actual life detection at locales beyond Earth in the solar system. to determine whether or not we have evidence for past or existing life elsewhere. I mentioned that we treated state of profession for the first time in our field in our survey. So I'll talk a little bit about our findings in that regard because we see them as broadly applicable across all of our communities. The committee identified the core principles listed below. The first being that broad access and participation is simply essential to excellence in our field. To the degree that we don't have those things, we are missing out on talent, great people, and great ideas. We find that substantial evidence shows that implicit biases can affect people's judgments, even among those that are sincerely committed to equal opportunity and treatment. And this motivates implementing processes to mitigate the effect of such biases. We found that implementing objective measures of self-examination in terms of the state of our field, the state of our profession are needed to support DEIA improvement and build community trust, and that we need a strong system of equity and accountability to recruit, retain, and nurture the best talent in our field, which of course is what we all want. Here are some of the main state of profession findings. The report acknowledges that substantial progress has been made, in particular with respect to the entry and prominence of women in the profession. However, as shown in the bottom plot on the right, much work remains, particularly to address persistent and troubling issues of representation by race and ethnicity. The report calls out the implementation of the dual anonymous peer review process at Space Telescope as a model for improving processes to mitigate bias, and noted that work-life balance issues are a major negative factor, in particular for different subgroups in our community. We have 4 main state of profession recommendations. Throughout this talk, you'll see the recommendations from the report paraphrased within these yellow boxes. The first theme for our state of profession recommendations was what we call an evidence-gathering imperative. That's a directive to our sponsors to place a priority on obtaining the information currently lacking on the state of our field and the climate in that field. And these are things essential to DEIA improvement. The second relates to the education of individuals and the improvement of processes to deal with bias. The third set of 4 recommendations address broadening opportunities to increase the involvement of underrepresented communities in our field, and the fourth to sustaining and ensuring a community free of hostility and harassment. So we have a whole chapter in the report on state of profession. It's followed by an entire chapter on the topic of basic research and analysis. The report makes a strong case that it is the basic research that takes these amazing results from the space missions that we do and translates those into an actual increase in the state of knowledge, which fundamentally is the reason for what we do. Among all of the RNA activities, the report highlights the openly competed RNA programs as the most impactful and efficient. That they are openly competed ensures broad access and supports entry in the field and DEIA. They're highly competitive, as all of us know, and that drives innovation. And the RNA program is also very flexible in its ability to respond to changing science and priorities. The Planetary program at NASA, shown in the upper right plot, has had an extraordinary past decade. You can see the colored chart showing the growth in the overall size of the budget, approximately doubling in the past decade. The investment in RNA per year has remained relatively flat when adjusted for inflation. The net result of that is that the fractional investment in RNA over the decade, shown by the red line, has decreased from about 15% down to about 8% currently. Along with that, as shown in the bottom plot, has been a growing field associated with the growing number of activities in our field, an increasing number of proposals, and a decreasing selection rate, which has been at or lower or below 20% for the last several years. And in this section, the astrobiology programs are specifically called out as having a quite low selection rate. So our main RNA recommendation is that this trend of decreasing proportionate investment in basic research really needs to be addressed to sustain and promote our field going forward, that it should be a minimum of 10% of the Planetary Science Directorate budget, division budget per year should be invested in RNA, and that this increase should be achieved by a progressive ramp up in the funding allocated to the openly competed programs. There are many other recommendations in this chapter as well that relate to the large programs, including ICAR, as well as defining RNA and RNA processes. Astrobiology, it's in the title of our decadal survey. Of course, as you can see, it figured prominently in our prioritizations. It is 3 of the 12 priority science questions, with a heavy emphasis, of course, in the exoplanets question as well. And as you will see, is a central goal of many of our current and planned missions. In the boxes here are 3 specific recommendations from the prior National Academy's Astrobiology Strategy for Search for Life in the Universe report. The first related to dynamic habitability, the second emphasizing the importance of study of subsurface life, and the third, a specific call for NASA to accelerate the development and validation of mission-ready life detection techniques. Speaking to that last bullet, we have a chapter in the report devoted to a discussion of technology development. It's a beautifully written chapter. I've excerpted a couple quotes related in particular to development of life detection technologies and the importance to integrate those approaches with sample acquisition, handling, and pre-processing system design to enable a single sample to be studied with multiple different life detection techniques. The overall technology recommendations you can see, the main one being that NASA should strive to invest a consistent 6 to 8% of its budget in technology development, and that it should have a technology program plan that both has a strategy and is transparent to the community, and that has a mechanism for community feedback. Okay, so now I'm going to turn to talking about planetary missions. We have 2 flagships, what we call the large missions underway right now. The first being Europa Clipper, an amazing mission that is scheduled to launch in 2024. Focused investigation of this amazing ocean world. I'm sure you're all familiar with this incredible object. It'll provide the critical foundation for our understanding of ocean worlds and their habitability. And we recommend that we strongly support this and recommend NASA continue development of this mission. The second large mission currently underway is Mars sample return. The Perseverance rover, shown on the upper right image, is currently selecting and caching samples at Mars. Mars sample return will bring those back to Earth. The top bullets talk about why the samples from Mars are so important to our understanding of primordial terrestrial planets and astrobiology in particular. You will hear more about that in the plenary talk tomorrow morning by Professor Minnie Wadhwa. But in short, Mars has a uniquely preserved primordial early sedimentary record. And it really is a unique opportunity to access information on the early conditions in the solar system, prebiotic conditions in chemistry, and perhaps, of course, also search for life. The report found that MSR should be the highest priority of NASA going forward, and it should be completed as soon as practically possible. There's a lot of support for the General Mars Exploration Program in the report, and for a ramp up of that program back to its pre-MSR levels once the peak spending of MSR has passed. And in particular, we recommend that the next medium class mission in that program be a mission like a Mars Life Explorer. This would characterize habitability of low latitude ice and look for modern biosignatures, in addition to evaluating the properties of the ice and the processes that lead to its creation and sustenance. Moving on now to the relationship between human explorations and science, the committee prioritizes what we think is a really exciting, groundbreaking human-robotic partnership at the Moon, the Endurance A mission. In general, detailed in a whole chapter on human exploration in our report, we find that the human exploration plans, Moon to Mars, are aspirational, inspirational, and we argue that they should be accompanied by a transformative scientific component that will provide a rationale for sustained human exploration and activities. So you can see in that top box our main overall recommendation that the Artemis Human Exploration Program should advance high-priority lunar science objectives as a key requirement. In particular, we recommend that the Lunar Discovery and Exploration Program make as its highest priority in the next decade enacting a medium-class mission, Endurance A. This would be a lunar rover that would be robotically delivered to the Moon's surface and then undergo a large, of order 1,000-kilometer traverse, collecting carefully selected samples along the way and return those samples to where they can be picked up and returned to Earth by the astronauts. And we argue that this would be the ideal synergy between NASA's historic Artemis human exploration effort and conducting transformative breakthrough science about not only the Moon, but the early history of the solar system recorded in its most ancient impact basin, South Pole Aiken. Let me move on to our New Frontiers program. Those are our medium-class missions that are PI-led, but each mission proposal has to address one of a list of pre-specified mission themes. For the New Frontiers 6 call, the committee prioritized 8 themes and one additional theme for the New Frontiers 7 call based on the factors listed below, the main one being their ability to address the priority science questions and produce breakthrough science. So here are those themes. These are just a phenomenal set of missions. We're very excited by these. Alphabetical order, the top group, upper left, a Centaur, orbiter and lander. Centaurs are objects originally formed in the Kuiper Belt that now orbit in the giant planet region and are thought to be primordial objects. Ceres sample return. Ceres is the most ice-rich object in the inner solar system. It's a dwarf planet. This would bring samples back from Ceres for detailed compositional and isotopic analysis. Also another sample return mission, a comet sample return. Of course, these are highly evolved objects. This would teach us about how they formed and evolved, in addition to telling us more about how comets contributed organics and water to Earth. Enceladus multiple flyby. Enceladus is an amazing inner moon of Saturn that has an active south polar region with plumes that are being ejected from its subsurface ocean. This mission would fly through those plumes and sample them. Lunar Geophysical Network, surface geophysical packages to teach us about the moon's bulk composition interior, Saturn probe to teach us about the composition and atmospheric properties of Saturn that help constrain where and when it formed. The Titan orbiter, we of course have the amazing Dragonfly New Frontiers mission underway. This would be a complement to that. This would be a global focused mission to look at the global climate and hydrological cycles as well as the interior of Titan. Venus In Situ Explorer, focusing in particular on surface and surface atmospheric interactions that can't be addressed by an orbiter or a single atmospheric probe. And finally, Triton Ocean World Surveyor. Neptune's irregular satellite Triton is this amazing moon that may be an ocean world and we know has plumes, and this mission would go into orbit around Neptune and undergo many tens of flybys past this fascinating objects. For our large or flagship class priorities for the next decade, we considered 6 candidates shown here as all having exceptional scientific merit. Ultimately, the ice giant orbiter and probe topic was judged to be the highest priority, primarily for its ability to produce transformative science on a class of objects that's the only one that we haven't studied with a dedicated orbital tour in our solar system. And again, we now think that these mini Neptunes to Neptune-class planets are probably the most frequently occurring planets in the universe. Another consideration here was that the multi-target system-wide emphasis of an ice giant orbiter and tour was seen as complementary to the current flagships which focus on single objects. We prioritize as the top priority the Uranus orbiter and probe. This would be an in situ probe to the planet, a multi-year orbital tour. You can see the topics to be addressed in the here on the right. The reason we carefully evaluated both Uranus and Neptune as potential targets for an ice giant mission. Uranus won out for technical readiness issues. At Uranus, we have a mission concept that's ready to start now. No new technologies are required, and we have viable trajectories on currently available launch vehicles. In particular, in our recommended budget, we argue for the start in FY24 of this mission to take advantage of a launch in 2031 to 2032 that can use a Jupiter gravity assist to get to Uranus with a shorter cruise length. We also prioritize a second flagship, the Enceladus Orbilander. And this is to address the question, is Enceladus inhabited? This is really a life detection focused mission. The report argues that Enceladus is the optimal locale to sample the subsurface ocean through freshly ejected material. And you'll note that Enceladus is the target of both our second priority flagship, and it was on that New Frontiers mission list I just described earlier. Ultimately, the committee felt that the study of Enceladus and life detection at Enceladus was such a high priority that we wanted to provide two different alternatives for making progress on that topic during this decade. So if Orbilander is initiated, and of course we would love to get a second flagship, then Enceladus multiple flyby would then be removed from the New Frontiers 6 and 7 list. So I wanted to speak for a moment about why the committee ended up prioritizing Enceladus Orbilander over Europa Lander, Europa being, of course, another incredibly scientifically compelling object. There were two main reasons for this. The first is what we know to be the accessibility of fresh material from the oceans at Enceladus, where we know we have well-characterized plume activity, it's continuous, relatively large amount of material. The second main factor is the benign radiation environment at Enceladus, which essentially allows for an order of magnitude longer mission to study and to try to detect life using multiple complementary techniques. At Europa, after being in orbit around Europa and flying through the plumes and sampling that way, we can land on the surface and passively collect material as the plumes rain down on us, in addition to having an active scoop in an overall mission that can last years. So we're extremely excited about the prospects for Orbilander, but I want to also do another call out for Europa, because we know that Europa Clipper is going to just be returning fantastic results and will transform our understanding of that object in the next decade as well. Let me finish by talking about some of our specific budgets. One of our requirements in our statement of task is what we propose has to be achievable within realistic budgets. We detailed two programs, the LEVEL program, which takes the FY23 Planetary Science Division budget and inflates it at 2% per year for the decade, and a recommended program that increases the total budget across the decade by a little less than 20%. The recommended program is really the one that hits all of the goals of the survey, and it's what we strongly recommend, as the name implies. But the LEVEL program, we were very careful to prioritize funding to yield a balanced, really strong program, even in that case. In the recommended program, here are key aspects to highlight a couple. The Uranus orbiter and probe gets initiated in FY24. You can see a New Frontiers 5 selection, as well as two New Frontiers selections in New Frontiers 6, rather. And the bottom point in particular initiates the second flagship, Enceladus Orbilander in FY29. The level program does many of the same things. Those are shown in white. The yellow points show you the differences. The start of the new flagship is delayed. There's no new start for Orbilander. But again, still an overall robust program. So this is my final slide, and then we'll hopefully have lots of time for Q&A. After we had done our prioritization of missions, we went back and created this traceability matrix of sorts to see how well they addressed our originally defined 12 priority science questions. And you can see the result here. Once we had completed this exercise, we thought that this suite of missions does an excellent job of addressing the breadth of the science questions. But we do want to highlight that we didn't actually start with this matrix to prioritize our missions, and that the boxes that are filled in should not be added up to prioritize one mission over another, because indeed, a mission that addresses just one question in a uniquely impactful way can be as important as another that addresses many. So you can see the questions 9 through 12, really, which is where most of the astrobiology emphasis lies, are an important focus of our recommended portfolio for the next decade. So those are our slides, and looks like we'll have about 30 minutes for questions. So thank you very much. Yes.
Hi, Sam Howell, JPL. I just had a couple of thoughts on this trade between Enceladus and Europa landers and some things I've been thinking about since the Decadal. So you mentioned that one of the driving differentiators is that we understand fresh plume material is raining down on Enceladus from the ocean. But I don't know that it's the community consensus that there is a direct and sustained connection to the ocean that results in rapid ascension, right? We have an idea that they're interrelated, but magnetic plumbing is complicated. And you mentioned the difficulty of Europa's radiation environment, but right, that's precisely why we want to study Europa, because Io plus ice plus radiation makes oxidants. A young surface brings stuff to a reduced ocean. And so, as you mentioned, we know that there's going to be fantastic science coming out of Europa Clipper, but it seems like setting a sort of 30-year goal of landing on Enceladus reduces our ability to respond to that science when we think about the best targets for landing, including what we might learn about Europa blooms. And right, so Enceladus gets an additional New Frontiers study, but the Europa lander flagship wasn't reevaluated as whether it in the New Frontiers cost cap. So I'm just wondering a little bit about whether or not there is a path to continue trading the science, because it seems like some of the best parts of the science for Europa weren't given the same consideration as for Enceladus, and we have a flagship going there this decade. So I guess summarizing that into a question is, when we think about the best targets for landing, is at the conclusion of the Decadal that as of today, the science that we should use to guide 30 years of exploration is settled and points to Enceladus? Or is there still room this decade to continue thinking about that?
Okay. Well, first of all, you will get no argument from anyone on the committee about the inherent interest and amazing properties of Europa. Okay, this is an absolutely fantastic target. Everyone is thrilled to see what Europa Clipper is going to bring back in terms of understanding. And these are both phenomenal ocean worlds. As you note, even though we have a lot of knowledge from Cassini about Enceladus in terms of plume location, plume volume, at the levels accessible with the relatively high sample collection velocities associated with Cassini, we do have knowledge of the smaller organic molecules. That knowledge is not complete, but it's very compelling. So it's that combined with the depth to the ocean in Enceladus, which we do have a pretty good handle on from Cassini gravity and associated studies, as well as the much longer mission survivability time that made this distinction. And that was the basis of the committee's thinking. With that said, every decadal is the assessment of the state of knowledge at the time the decadal survey is written. You know, in other areas, we've already seen things happen that have changed relative to what we considered just since the middle of April, okay? So hopefully what we do with the decadal survey is we lay out the rationale. The core rationale is the science. The core rationale are the science questions, okay? And we make our prioritizations based on the state of knowledge of the time. But as things evolve, if we've done our job right, those core science issues will still be there to provide a framework if needed by the change of events or a change in budgets or changing discoveries for things to respond. For instance, we saw in the last decade, right? We didn't even have an Ocean World's New Frontiers theme from Vision and Voyages, right? That was an addition in response to evolving scientific knowledge and excitement that happened during the decade. So, of course, no decadal is meant to constrain things for 30 years. And in fact, if it's done well, it will provide a framework to even within the decade, if needed, to allow our community and our sponsors to respond to those changes.
Thank you. I appreciate that.
Hey, Robin, Morgan Cable, JPL. Thank you so much for giving this briefing, and thank you also for your service in leading the survey.
Thank you.
I have another question about Ocean Worlds, if you're willing to entertain one more.
Yeah.
I was wondering if you could clarify a bit the plan for Enceladus. You had mentioned that it was important to keep both options open of New Frontiers and Flagship, and that if the Flagship did receive a new start, that Enceladus would be removed from the New Frontiers list. My question is, what if the converse happens? What if the Enceladus multiple flyby mission is selected for New Frontiers 5? What does that mean for the Flagship?
That's a very good question. And I think that, you know, that would be, it's not actually specifically addressed in our report. We thought that the trajectory of the decadal budget would be accessible, or you would be able to make some assessment as to whether or not an Orbilander flagship this decade was viable enough relatively early on. After the decadal survey was released, the president's budget came out, and one of the things that budget did was it moved up the New Frontiers 5 competition by several years. In general, of course, we are all so happy to hear that, because New Frontiers was falling behind in its cadence relative to that recommended by the decadal surveys. So we're very happy about that. But you know, my sense would be that it would be up to NASA to decide, but the arguments in the report would probably favor doing one rather than both.
Thank you.
Although that's not specifically addressed in the report, the situation you described.
So just understand, if a team were considering proposing an Enceladus mission for NF5, that could put the flagship at risk later on? Is that, just trying to understand? I don't want to put words in your mouth, I apologize.
Yeah, I don't know that I agree with that. I mean, I
Okay.
think what we've seen in the history of just fundamentally compelling objects is that the more we think about them, the more we propose them, the more we come up with ways to address them. First of all, we bring them more attention, and we bring more weight to doing more there. And sometimes we conceive of approaches that our committee in 2 years didn't think of. You know, that's always something that you hope, right? That there'll be new great ideas out there inspired by proposers.
Thanks, Robin.
Thanks, and thank you, Morgan.
Hi, Casey Dreyer, the Planetary Society. One very quick process question. Really enjoyed the chapter on workforce and really important chapter. For me, at least, it was a little hard to take away the full narrative of that chapter because a lot of the charts were missing from the published report. And I was wondering if there was any sense of a timeline of when we can expect that visual aspect of that chapter to be published and represented.
So the figures that are currently not in the released version are withheld due to copyright issues. Those are currently being the copyright permissions are currently being sought on a one-by-one basis, and we're looking at probably midsummer, hopefully mid to late summer,
Okay.
to have the full copy out with all the figures. And I must say, as a shout out to Paul Barron and James Keen Tuttle, the figures, many of which they were involved with, are actually gorgeous. In addition to the graphs and plots, the actual the figures and the schematics are really beautiful. So I encourage everyone to look at that full report with the figures in it once it comes out.
Thank you. I'll look forward to that in the summer. My other question was about the science questions that was listed and included in the report. And I'm curious about how the committee approached that from a sense of, are these, to me, it seemed like very fundamental types of questions facing the field versus questions of what you would achieve in 10 years necessarily. Is that an accurate way to reflect that? Or do you see these as questions that will be driving fundamental, I guess, for lack of a better term, solutions or serious advancements, and then you'd have a different set of questions pertinent to the next decadal survey?
That's an excellent question. And we approached defining the questions by trying to identify broad cross-cutting questions that should, perhaps with some minor modification due to advances in the next decade, be able to carry forward across decades. In other words, we started off specifically by asking the steering group members to each identify a handful of what they saw were the prime motivating questions that we are trying to solve as our field. Nothing narrow, nothing related to a specific object, but the big cross-cutting questions. So then we gathered all of those. And even with that initial input, it was clear that these three themes of origins, processes, life, and habitability came out very early on with exoplanets as well. Then we tried, and then our follow-up exercise was, well, how many questions? And we discussed things like we didn't want them to be so broad that you would end up with only a couple overall, and it would be hard to distinguish between different activities. But we didn't want them to be so narrow that they corresponded to just a single object. So you saw where the compromise ended up, and after we had put together those, I think I might even have this. After we had put together our questions and looked at their topical distribution, and so that's the pie chart on the left, including the two really science-oriented chapters, Human Exploration and Planetary Defense. We did that all independently. We didn't look at the prior decadal, really. We didn't look at any other input. That was purely the steering group with feedback from the from the panels, rather. After that, we went back and looked at the big picture priority questions that the ag groups, the assessment groups, LEAG, MAPSET, MEPAG, OPAG, SPAG, MEXAG, VEXAG, had generated in response to a request from Lori Glaze to do so about a year before the decadal started. And then we looked at their distribution of topics, and you can see it almost looks like we started with theirs, even though we didn't. And so at that point, this gave us confidence that we had the right distribution of the questions by number across these topics. In terms of the specific sub-questions and strategic research, we think those will evolve from decade to decade. Okay. And the strategic research activities were defined so as to maximize progress in the next decade, with that as the guide.
Yeah, thank you. I mean, just to unite two parts of my questions. It almost seems like these questions, pursuing them defines what the workforce is to be a planetary scientist, defines the bounds of the field, right? So if you were working to answer one of these questions, you're a planetary scientist.
Yes.
And then would be part of that workforce discussion.
Yep.
Yeah, thank you.
Absolutely. Thank you.
Hi, thank you very much for this presentation. So I have a question about the research and analysis section of the reports. So here, the reports mentions high risk, high impact proposals may be disadvantaged by the proposal review process. And then there is a recommendation that NASA should ensure an appropriate balance between a high and low risk proposal, and the risks being in terms of exploration of novel ideas and techniques. So my question is simple. What such an appropriate balance should look like in your opinion? So it's a broad question.
Sure, sure. So, so one of the issues, and I think anyone that has reviewed and submitted RNA proposals will probably be familiar with this effect, and that is that proposals that use established techniques, that pursue well-accepted hypotheses, tend to have an advantage over ones that are doing something that goes against that standard grain, either in thinking or technique. It's just kind of the way the peer review process can work sometimes. And so the part of the RNA chapter that you mentioned is encouraging NASA, because they've already been doing so. They already have been looking into how to make sure that these high risk, and risk can be several different things in this context, but high potential reward activities, to make sure they're funded. We encourage them to continue to do so, and to evaluate the balance of more traditional versus higher risk, higher impact activities. We didn't actually prescribe a particular balance of those two. One thing that you'll see in the RNA chapter is that we establish what we think are the important principles, but by design, we've left NASA with a lot of flexibility on exactly how to implement processes to achieve those goals. And the data we were able to obtain on the RNA programs currently, on what they produce, on the balance of high risk versus low risk things that are funded versus proposed, was not sufficient and complete enough to do that kind of analysis either.
Okay, thank you very much.
Okay, thank you.
Hi, thank you for your service for the Decadal. In hindsight, is there anything in the statement of work that you thought was extraneous, and anything that you think should have been included in the statement of work once y'all were working on it? Like, was it a good balance? Or it's all great?
This will sound glib. I don't mean it to. There were times when one wished the statement of task was less broad.
Right.
But that wasn't because it wasn't appropriately broad. It was just under the weight of everything that had to be done during a single decadal process, because the scope was quite large. But no, I don't think I can think of anything that was seen as being inappropriate, or that we discussed that should be added. You know, there are topical transitions that occur. For example, exoplanets is one of them, between the astrophysical decadal and the planetary science decadal. I thought that transition in our statement of task was handled very well. We didn't cover anything related to exoplanet detection, but in terms of comparative planetology and what the study of our solar system can tell us about exoplanets, and what studying exodisk and exoplanets can teach us about our solar system, that was within scope, and I thought that fit in very well with our science questions. So yeah, I don't know that I see any. I think that the statement of task was very well posed, actually.
Great, thank you.
Yeah, Bethany Teeling, NASA Goddard. This was a great presentation. I've seen it a couple of times now, so I really appreciate each time I see it. I was actually wondering, because the two recommended flagships are outer solar system missions, do you all give any recommendations, especially concrete recommendations, on how we can recruit and train the generation of scientists and engineers who are actually going to do these things?
Well, of course, the identifying, recruiting, retaining, nurturing the best people in our field overall, that's really the heart of the State of Profession chapter, right? In addition, the openly competed RNA programs, I mean, this was really the core of that whole chapter and that recommendation to substantially increase investment of RNA. It's to both get our workforce in place to handle the new data coming in from things that are planned, but also the workforce we need to develop the new missions. Okay, it's very forward-looking as well. So the RNA program, while, as you can see, it's a small fraction of the overall PSD budget, we're arguing it for to increase from 8 to 10%, it's disproportionately where people enter the field. And that's why we place such an emphasis on it. And I should also mention that while the difference between 8 and 10% may sound like a small difference, it's not a small difference to the RNA program itself. So that difference is about a 40% increase in the openly competed programs. So we see both our state of profession recommendations and that increase in RNA, as well as, of course, the teams that will be supported by the missions themselves. But I think what you're getting to is really the workforce development issue more than those. So it's really that that increase in the RNA that we see as needed to, instead of a decreasing decline, get it on an even keel so it's proportionate with the overall program you're trying to develop and sustain.
Okay, thank you.
Yeah. And actually, and David Smith just reminded me of another recommendation related to your point, which is a small mission line known as Simplex. So our statement of task had us prioritizing only the medium and large class missions. But we do talk about the small mission programs. So Simplex is managed within the Discovery program, and it's currently a $50 million per call kind of mission, and it allows for a lot more risk, for new technologies to be developed, but it also allows for new investigators to be trained as well. And so we talk about its role in training that new generation of PIs and instrument scientists in the report. In addition, we have a recommendation that that cost cap be increased to 80 million for future Simplex calls. So thanks, David. That's right. Yeah.
Hi, thank you. This is Karen Rogers from Rensselaer Polytechnic. My question is getting back to scope, and I noticed in the scope of in the initial piece of the document that origins of life, origins and emergence was specifically stated as outside the scope. And while I understand that because 700 pages seems like a lot to write, I guess I'm wondering where you think that might sit, given that things like life and habitability, learning from terrestrial life, early planetary conditions and looking at biosignatures is really intimately tied with origins of life research. So where should it sit? It doesn't sit in exoplanet decadal. It doesn't sit in the planetary decadal. So where should it go?
Yeah. So David's going to be perhaps the more expert responder here. So I think her question pertains to the origin of life topic in particular, and the extent to which it's outside our scope, but naturally, of course, it's central to astrobiology, and indeed is supported by the astrobiology program. And so where should it fall in terms of decadals, do you think?
Well, currently the origins of life don't really fit into any of the decadal surveys. But that's not necessarily a bad thing. It just means that somebody should lobby the appropriate agencies to start up such an activity. So the closest thing I would think of is the report that Robin mentioned, the 2018 Astrobiology Strategy for the Search for Life in the Universe. That's probably the closest document that discusses the origins of life. The only other academy report I can think of that does that was written before you were born.
Yeah,
So
it was on that last.
The Search for Life's Origins, which is a fantastic report, but it was written in the 1980s.
Sure, and I was on that last one with you, so I appreciate that. Do you think this report on the planetary would be strengthened if origins were included?
Would it be strengthened if we considered
If it were part of the
it would have made a very complicated and large process that we ran even more complicated and larger. I think the survey as it stood from a managerial perspective was about as large as it could be. We had 97 people distributed amongst the panels and the steering group, and adding in, it might have been half a dozen of extra people, might have been the straw that broke the camel's back. The other danger of including things that are on the, since a lot of the stuff we were focusing on was related to missions, going places in the solar system, looking at objects beyond the solar system with telescopes, when you bring in stuff that's mainly focused on lab studies, you get these groups that feel as though they're dangling on the edge of the organizational chart and doesn't lead to a good process. So I think for origins of life studies, maybe the need there is for something separate. It may not be a decadal survey. It might be a science strategy that goes beyond what's in the existing astrobiology strategy. But certainly our old Committee on the Origins and Evolution of Life tried to start a study on the theories of the origins of life. And we could not even write down a statement of task because there were so many diverse groups pushing their ideas. And I think that field needs to get itself a bit more organized than it is currently before they could even attempt something as big as a decadal survey.
Great.
And I think I've probably said too much.
Thanks, Dave. Thanks, Robin.
Thanks. All right.
Jen was up before me.
Jennifer Scully, JPL. So thank you for all your work on the Decadal survey. My question is about the recommendation to raise the New Frontiers and Discovery lifecycle cost caps. So I'm wondering if you can give us some more insights into the committee's rationale for that and any discussion that there might have been about how to balance that within a finite budget with respect to like number of selections and other budget priorities and things like that.
Yeah, so I didn't cover this in specific, but on this list, when the number of Discovery and New Frontier selections is listed here, that is at the new recommended cost caps, which are substantially larger. So an overall goal was to bring the cost structures and the cost caps for those programs more in line with the missions that have been recently selected and that frankly we are all thrilled about and want to see selected in the future. So at Discovery, we recommended raising that cap to 800 million, including phases A through F, to still retain the identity of the Discovery program as having a single cost cap, predictable cost that allows for high cadence, maximizing science per dollar at any target you can go to. But it's clear that the exciting Discovery missions picked in the last several rounds would not have been well supported by anything like the $500 million cost cap that Vision and Voyages had envisioned. And that program is evolving, right? We've addressed a lot of science. We have more ambitious goals and desires for instrumentation. On the New Frontier side of things, we recommended again a substantial increase in the phase A through F cost cap to 1.65 million. At New Frontiers, we also recommended that there be an addition to that cost cap. If memory serves, it's something like $30 million per year of quiet cruise phase, so that at New Frontiers, you maintain a constant level for your instrumentation and your actual mission once you get to your target, but that objects that require longer cruise in the solar system, be that because the objects are far away, or because you're going there and back again, because you're doing sample return, or you're going to the innermost solar system, that those be given a level playing field. And again, we were looking to Dragonfly and as an example of a phenomenal mission, just the type of mission that we see as being needed to address the priority science questions. With that said, when you raise the cost cap, you're going to have to account for it in the budget. And we did that very specifically. I don't think I showed sand charts, but you can see here part of our sand chart exercise for our recommended program. You see that New Frontiers and Discovery lines. You see Mars sample return, that new flagship number 1, that would be the Uranus. New flagship number 2 would be Orbilander. Okay, and so, so those cost caps were included in this planning. Okay, thanks. Hey, Brittany.
Yes, thanks again for the work.
Oh, I'm sorry. I'm supposed to tell you that this will be the last one, Brittany. Thanks. Okay, go ahead.
Luckily, there's no one behind me. So I wanted to return to this issue of the RNA program. So I thought the recommended increase was obviously something that we need to have. But kind of returning to the theme that Karen was striking, is that disproportionately astrobiology has recently been affected by the way that RNA programs were cut. In the last decadal survey, we said, please never cut anything in RNA or make RNA the last thing to cut. In the last 3 years, we've seen a pretty significant downturn in the RNA funding, and most especially in the area of astrobiology, which has seen cuts between 20 and 30%, despite the importance of the questions that you have in the decadal. So my worry is that by tying it to 10% of the budget, with the, I would say, aggressive budget that we've proposed here, which would be amazing if we could get it, it seems like tying that number then means that the RNA program is also going to go down if the program scale also comes down, which means you have fewer flight projects as well as less RNA money. So I wondered about the choice to tie it to the scale of the program and not to make stronger recommendations for it never falling below that, rather than being always 10%.
Sure.
Or something to that degree. Because as those flight projects stop happening, fewer scientists are supported. And then the worry there is because even in Simplex, which yes, trains perhaps new PIs, the size of the science team is smaller, which means it supports fewer younger scientists in general.
Yeah,
inside all
absolutely.
of these wedges. So,
It's targeted mentoring, essentially, of relatively small teams. So, all the issues you just brought up are very important in that RNA, and that thinking fed into that RNA recommendation. What I didn't show, and I guess I don't have it in my backup slides, are our overall decision rules for what should be done if the budget is constrained below that of the level budget. And in that list, which is essentially from the first thing that should be cut to the last, you'll find RNA is the last. So the minimum of 10% was identified, that word minimum is important. And within the text that precedes that recommendation is language that talks about the importance of stability, and that any changes in the overall program should be accommodated as gently and slowly as possible, with the workforce to be the last one to be changed. I think it is true that if something catastrophic were to happen and the program were to be, dramatically smaller than it is now, a smaller workforce would be needed by NASA, right? That's not something any of us even really want to think about. I hope that is not something that has any likelihood of happening, right? but between the percentage level investment and defining that as a minimum, and then having RNA as the last thing to be cut if things go below the level budget, those were our ways to address the issues you raised. Okay, thanks everyone. Have a great day. Thank you.